This is the agenda I'm going to go through. Seeing that I have 30 minutes, any one of these topics could probably take a day if we want to get into the details. So, first thing I wanted to go over in NVH is acronyms and buzzwords. Some names are familiar in the chat panel, but not everyone. So I don't know your level of experience or really where everyone's located. Based on your experience level, what industry you're in, what software you use, some of these are going to be slightly different. I have friends of mine that like to talk about physical responses. They always call it tactile response. There are those who, if you work just in acoustics, it's going to be very product specific, and you'll see words such as porosity, tortuosity, biot, that may be kind of puzzling to someone who doesn't do acoustics. So I'm going to use what I think is like 80% of the acronyms, buzzwords, and phrases throughout this discussion. You may know something different, but there's no reason to think that there's some new hidden thing out there that someone's hiding from you when they use a new buzzword. You'll probably see more of these and new ones coming out with the increased use in plastics and composites, which are driven by the new MPG standards. So, one other point that I'll make throughout this discussion based on my experience is that the GUI, or the graphical interface that you use to pre and post, doesn't make up for a lack of knowledge. There is artificial intelligence built into it, and it's there just to reduce your repetitive work, but it doesn't replace, basic knowledge on this stuff. So, my experience NVH over the years has evolved in that the H has kind of dropped out of NVH. When I go into the auto OEMs, their groups tend to be named N&V now. And underneath will be your overall group names. There's a body group, ride handling, systems group. They even may break the body up into two different ones depending on the trim level in the vehicle. Body in prime, body in white, trim body. Ride and handling has somewhat taken over the harshness work. So they're a separate type of analysis that goes on using atoms. So with NVH, what do you do? How do you do this? Years ago, it was physical test. To give you a perspective, a real long perspective, I remember watching a film at General Motors where one of the original crash testing back in the 40s, the driver would stand on the running board of the vehicle and guide it towards the crash barrier, and he would jump off at the last minute and be caught by his co-workers before the car continued on and crashed. Obviously, we don't do that anymore. We still do physical test. The idea, though, is to replace it with CAE analysis. The goal, of course, is one test to validate when it's required. There are some CAE work, at the very basic level, that analysis is perfectly fine. Then when we get into simulation codes, FEM, multi-body dynamics. For us, it's Marc, Nastran, atoms. All of these solutions that I've listed out here, everybody knows what these are, normal modes and so on. They are always part of the CAE work. Most of it is normal modes and statics. Then it moves up to the dynamics. You're always going to do transient response when you're looking at fatigue. Frequency response, including acoustics that's the noise and vibration part. That's the main piece. There are those who do complex eigenvalue analysis and random responses. Those tend to be a little specialized. Then there's things, super elements, transfer functions, optimization, a little more specialized, but it's still part of the N&V process. Then there's the test analysis correlation. And NVH, NNV, whatever you like to call it. There's always the individuals who've never done the work and want to know why your analysis doesn't fall right on top of the test results. Well, you're not, those who have been in both worlds, test and analysis, know that that's not possible. Every time you run that test vehicle down the test track, even with the most controlled conditions and the best driver that you have in the fleet, there's going to be slight variations. CAE is going to give you the same answer every single time. That's just because it's numerics and it's computers. Acoustic codes, and for us it's Actran. Nastran's always been able to do the internal acoustics, and that's important. Driver's right ear and so on. The vehicles have gotten very quiet and handle very well. Of course, it depends on the trim line or what vehicle you buy, whether you're down at your entry level or you can spend $100,000 on a vehicle. And most of it's the interior, what you hear. It's become more important for exterior. Where does the noise source come from? Wind noise on the mirror. CFD for fans, what you hear when it comes out of the outlet. And where's the source? I guess it's mechanical. The engine, which really is a big problem now, is because they've gotten things so quiet that now it's the powertrain that's a noise source. Direct fuel injection. The injectors, of course, run on high pressure fuel. Their opening and closing actually gives you a ticking type noise, which can be amplified when you go through a drive-thru. And the responses, obviously, your human error. The rear passenger compartment, which at one time was, all right, they would test for that stuff and do some analysis and support it. Now it's become just as important as what does the driver hear. Then there's external microphone location. There are not only you want to keep things quiet on the outside, on a high-end vehicle, even the gurgling of gas going into the tank is something that they're concerned about. Now the NNV is not just automotive. It has expanded outwards into regular industry. Those of you who are not in automotive who are listening to this, within factories, construction equipment, there's the OSHA requirements, here in the United States, overseas. I know there's government requirements for noise emissions, and that is, microphone locations, how much do you measure in dB, and there's limits on that. Again, I bring up the interfaces. This is how NNV has been pushed out into the masses for more and more individuals to start using. Is you embed some of the common practices in there so that you can run these things and help interpret the results. We'll talk about model size here shortly. But you have to know essentially all this stuff and how it interacts if you're going to be a good at NNV person and make the most of it. Because the interfaces help you, but they don't replace knowledge on the engineering. So performance. Model sizes go up. That's just a natural. Computer power increases while cost decreases. I recently heard that back in the day, a Cray C90 was leased at $1 million a month. Now your laptop, the one that I'm working on, probably $2,000, $2,500. And comparably, I can solve the same model sizes on my laptop as that C90. So there's this big difference in the hardware cost, how it's come down. Then there is the pressure to artificial intelligence, the CAE process. Push it out so everybody can use it. In the CAE, what we have in our solvers, and I'm including MSC Nastran, Marc, Adams, and Actran, all of these things that I list down here, they aren't in every one of the codes, but most of these solvers and so on are in every one of our codes. And we have multiple solvers because we have to. The defaults within the solvers that we put out typically are good for anything that the NNV throws at it, but there are those models and situations on the extremes where we have to have several solvers, whether it's the sparse solver. Metis is one of the buzzwords, or there's extreme. Cassie is an iterative solver, great for solid elements, not so great for shells. We offer all of these, and we include within there, the different ways of breaking things up to use all of those cores that you can buy. A CPU, standard is what, 2-4 cores? You want to use those with memory, shared memory parallel, distributed memory. You break the model up into pieces. It's one of the favorites for nonlinear analysis. They call it DDM. You got to tie them together so they can work together. NVIDIA has the GPUs, and we support those in most of our codes. Then there's the specialized stuff that within Nastran, the buzzword SMEM. Well, that's just a hard disk up in memory. And if you have a flash memory, it's extremely fast, reduces wall clock time. So as the models get larger, you expect to have turnaround time within a day. That's the standard. And this is how we support that for you. Our performance in every one of our releases, it's published in the release guide. Very few people read these things, and it's rather boring because it's just a bar chart. And over multiple releases, the changes or the performance increases are drastic. I give you here an example of, here's from probably 15, 20 years ago, version 68 to 69 for Nastran. They reported percent improvements. Model size of 1.9 million degrees of freedom, which was fantastically large. Over on the upper right, might be difficult to see, but here's a large automotive example at 7.3 million degrees of freedom. We're solving this in minutes for frequency response. Then down below here, because of the improvements between version 2010 to 2012, on the left-hand side, we express the time in hours for wall clock. And we've gotten so fast that now we've got to do it in minutes. And these are comparatively the same models. So performance-wise, we are keeping up with stuff. We offer that for the NNV crowd or anyone else who uses Nastran. They are in there. If you're not using the latest release, you should be. I just recently worked with a large powertrain model that is probably 16, 17 million degrees of freedom at the analysis set, not the G set. And version 68, it solves in 64 hours. And in version 2012.1, we've got it down to 35 hours. So in automotive, Nastran has been around since 1974. Those who remember the Chevrolet Vega from many years ago, that was at General Motors the first finite element model that they did with Nastran. It was a stick model, very simple. It has set the standard. It's been around for a long time. Very reliable. We always fix we're always constantly fixing and improving things inside there. Users always are inventive and discover things that we haven't thought of. The data format, whether it's ASCII or binary, that's sometimes like the punch file and the OP2, people write it, our competitors write it, they read it, because it's a standard format. It's typically used for normal modes, dynamics. Optimization has gotten very powerful. These last three, restarts, DMAP, and the aerospace, there are times when aerospace solutions have crept into the automotive area. Restarts have fallen out of favor because the computers have gotten very reliable. But when it comes to these very large models and restarting into the modal solution space for the dynamics, when you're doing 60,000 restarts a year, it makes a big difference when you don't have to calculate those modes 60,000 times. And DMAP lets you get into the code. Many people use it to insert their own solvers or their own techniques. and actually commercially sell that DMAP to the end users and companies. We have moved up to, because of the Marc acquisition, Nastran has true 3D linear glued contact in all the linear solution sequences, and the Statics has nonlinear. Again, this is something that helps on the N&B side, where meshes don't have to be, synced and lined up anymore. We added the solution sequence 400, which is a subset of the Marc nonlinear for the Nastran users. So your interface, you're used to Nastran, you're still using it. There was no reason to rewrite the old nonlinear solution, simply because the way they were written, very inefficient. It was better to start from scratch again. Optimization, the favorites, the topo favorites are in there. We can do MDO, so you can incorporate crash. There are several ways to do that. Composites are going to be very popular. We've had composites in there for the past 5-6 years. I mean, we've had it there for a long time, but it's got dramatic improvement because of aerospace and the Boeing composite work. Many people in NV don't know about that because they haven't been forced to use it, but we have it. It's already there and ready to go. Now with Marc was the original nonlinear finite element solver. It's capable of solving some very large problems. The solvers inside of there, some of them have gone into Nastran, some of ours have gone into Marc. It's got this automated nonlinear contact. This is the most important thing, is that you don't have to, for the NV person, you have to do these contact pairs or figure out who's going to touch who. The code does it for you very efficiently. And there's this automated remeshing. I've got some examples here to show you why it's important. Contact bodies, again, Marc, even in Nastran, because we have this contact bodies, every one of these colors is a contact body. We don't care about the elements. We'll figure out the contact faces or the element faces. This greatly improves and speeds up the N&B process if you have to do these door latch. This is one example, or gaskets and so on. Here's the automatic remeshing. Now this is not automotive, but it's extremely important to note that this automatic remeshing stops you, it eliminates the bad element that comes from highly distorted elements. And this is a Marc feature. It is not in Nastran. Here's self-contact with the automatic remeshing. This is a highly nonlinear problem that's very difficult to solve. Marc solves it with very little effort, and little effort on your part to set it up inside the Mentat interface. Atoms, again, automatic dynamic analysis mechanical systems. I've shown you several things that we can do within the automotive workspace, and also, of course, aerospace too. Nonlinear motion, again, all this stuff talks to each other. It is Nastran can send models over to atoms in what they call modal neutral files. They can essentially send back the atoms model in a linearized state back to Nastran for it to be used. It's also integrated that even Marc can send things back and forth to atoms. So it's all put together, and of course we've got fatigue is embedded in there, the MSC fatigue product. Now, it says NVH has gone across, and not only is it automotive, that's why I left the shovel there as the center. There are NV requirements for off-road vehicles, for large trucks and so on. Probably more harshness and vibration and noise levels are much higher there. We can integrate with atoms, the hydraulics control system. You can have test rigs for durability fatigue. If you need to get down to powertrain driveline, we have it in there. And then there's packaging. Not only, you think of packaging of what you buy at the store, things that are packaged in there, but packaging as to, where are you going to put things within the automotive design so it doesn't interfere with each other. We've added with Adams the automatic flex body generation. Again, this is the AI and the interface that I talk about, where you have someone who's very well versed in Adams and does not touch the finite element stuff very much. You can pick out one of these pieces, say build a flex body. We'll go off and do it in the background for you, so you don't have to learn how to use Nastran or Marc or whatever to build that flex body. Obviously, you can't. This isn't set up for when you bring a huge trim body into an Adams simulation, but as a starting point for the individual pieces, this makes it much easier. We've added wizards for just recently, these Adams machinery for chain drive systems, belt drives, and gears. These are extremely time-consuming to build for an Adams person, and you have to be somewhat a high-end to get this to work right. By putting these wizards in there, we brought it down to a point where most Adams users can do this, and the time goes from 5 days for an experienced person down to 1 day for someone who's taken some training and picked it up and wants to do this type of analysis. Again, this goes in with the NNV problem that's matured today to the point where its powertrain is a noise. It's no longer noise coming from other areas. It's now the powertrain because we've got things so quiet. Acoustics, and I say this is the best for last because Actran is a very good product, and it's used for all types of acoustic work. And how your acoustics you're going to look at depends on the vehicle. Over-the-road truck versus this Mercedes, or over here on the right, you've got the Ford Focus. Up in the left, the new Camaro. When it comes to acoustics, individuals that you're selling to expect certain noises, and they expect non-certain noises. In some cases, there are, they call sound tubes that run from the intake to the firewall, so that on a high-performance vehicle, you hear the noise of the engine. The person who buys the vehicle is expecting that. Of course, then there's also the environment, too, that you're going to go over. Most of the time, it's the highway over there on the left. Over on the right, the off-road vehicle, they aren't too much concerned about acoustics. So the Actran Solver Suite out there, they have their own interface, Actran VI. What I have circled here, I doubt we'll ever have to deal with that at NNV in the automotive or ground vehicle. That's for engines, turbine engines, and so on. But along the bottom here, what we're looking at on the left is acoustic radiation from your powertrain. In the middle, that's an air intake box with the CFD flowing through there. What noise is being emanated from that? And on the right, that's another powertrain acoustics. On the next level, we've got vibroacoustics, aeroacoustics. So it's fan noise, either from the CFD, which is the Actran Aeroacoustics, or vibroacoustics, the vibration input into the system and what is emanating out of there that you would hear. At the very top, Actran for Nastran. It's a two-way communication. They can read the Nastran data deck. Don't have to learn anything new. They have a very good interface for, again, bringing the experience to everyone's level. You can solve things in Actran, or you can send it back to Nastran. It doesn't matter either way that you want to go. Some of examples. Again, here's a close-up of a powertrain with a mesh around there. What do you want to measure? You want to measure the noise coming out of it. And the waterfall plot. That's for powertrain people want to see this as the frequency goes up so they can identify the modes that are a problem. So any vibrating or radiating component they can do in Actran. We can send back to Nastran, again with Actran for Nastran, the trim components, your carpeting, headliner, and so on. I mean, the Nastran models are really big, and sometimes it's better to do the analysis in Nastran rather than in Actran. We don't constrict you to either one of those. We let you choose. Vibroacoustics, again, gas tanks. We can fill the gas tank with fluid using our Solution 700, which is Ditran and LS-Dyna combined together. Use that vibrational noise to send back to Actran, and then measure with microphones, what do you hear as this thing's being filled? You would not think that that's an important feature in NV, but it actually is. It's something that we've been asked to do, and we can do it. Other NV applications. And here's the microphones and field mesh. Very easy to build. Down here in the bottom, we've got the exhaust system. That outer shell that's being pointed to here, the heat shield that's over the converter and over the muffler to keep that thermal from getting to the passenger compartment has to be designed carefully because it can actually be a noise radiator, and Actran can help you design and figure out if it's going to be a problem or not. Then again, with the exhaust, with the outlet, that is the exhaust pressure coming out, what do you hear in the vehicle when that's going on? And Actran can help take care of that in the NV thing. All right. So I tried to keep this short because I would suspect there is a lot of questions.